All right, let's get into this lesson on quadratic methods. So when you see the title quadratic methods, you might kind of wonder what we're talking about here. Basically, what I want to look at is to say, let's look at problem solving techniques that utilize what we know about quadratics. So we're going to try to solve problems that might lead us to quadratic equations. And so given a quadratic equation, one of the things we want to do is to say, we've talked about a few different methods of solving quadratic equations. Given a quadratic equation, which method do you think I should use? So what we want to do is we want to kind of come up with an order to say, what's the easiest thing that we learn? So we learned three different ways of solving quadratic equations. We learned the square root property, we learned the zero factor property, and we've learned the quadratic formula. So let me remind you what each of these are, and those are in order of easiest to hardest. So what's typically going to be the easiest thing is if you can use the square root property, where the square root property is that property that says if I have a perfect square on one side and a number on the other, then I can take the positive and negative square root of both sides. So that one's the easiest because that gets us pretty much right to our answer in a single step. So if you can easily get a perfect square on one side and number on the other, that's what you want to use. Now, if you can't easily get a perfect square on one side, number on the other, then you're going to fall back on one of the other two methods, and both of the other two methods require you to have everything on one side and a zero on the other side. So if you can't easily get perfect square on one side, number on the other, then get everything to one side, so the other side is zero. Now, once you have everything to one side and the other side is zero, try to factor. So if you're able to factor, do so. And that's what we call the zero factor property, is when you have a quadratic that's factored as parenthesis times parenthesis. You say either the first parenthesis is zero or the second parenthesis is zero. That's the zero factor property. Now, when I say can you factor, I really should say can you factor easily. Because if the factoring is ridiculously hard, you could always fall back on the quadratic formula. But factoring is going to lead you to less errors because you're not doing the whole b squared minus 4ac and square root and all these places where errors happen. That if your factoring is pretty straightforward, definitely go that route. The quadratic formula should be your safety net. It should be the last thing you try, but it will always work. So those other guys kind of worked in special situations, that the square root property, he works when you have a perfect square on one side, number on the other. Otherwise, you have got to do the whole completing the square thing, at which point you may as well use the quadratic formula. Now, if it's factorable, that's another special form. But again, if neither of those special forms work out, quadratic formula always will. He's the catch-all. But we try him last because the other ones are easier. They're fewer steps. When I say easy, that's really what I mean. They're fewer steps. And by them being fewer steps, you're less likely to make an error. So that's the process. So how are we going to go about in this lesson solving problems and approaching problems that we need that reasoning for? Well, we're basically going to do three types of problems in this section. I'm going to start off with some review. And by review, it's not fully review. We're going to look at some old material, things that we did previously that led us to quadratic equations. But in the past, those quadratic equations were always factorable because that's what you knew how to do. So now we're going to do some review and say, all right, well, where do we get quadratic equations that pop up? Maybe these aren't factorable. Maybe I have to use the quadratic formula. So we're going to review some of those. And this will be actually helpful as we're starting to get further into the course. It'll be a good way to look back and say, let's do some final exam review right here is kind of what's going on. So we're going to review a little bit of things that led to quadratic equations. We're also going to introduce this topic called U substitution, where U substitution is going to be a way that we can camouflage a problem into a quadratic. So we're going to start with a problem that isn't really a quadratic. It really doesn't have an x squared and an x and a constant. But it's going to have some sort of algebraic function, and then that function squared. And so at that point, we're going to say, well, this sort of looks quadratic-y in the sense that there's something and then something squared. So what we're going to do is we're going to do a substitution that makes it into an honest-to-goodness quadratic, where we literally have a u and a u squared, which means we can use our quadratic formula or factoring or the square root property to solve that quadratic. And then once we've solved the quadratic, we're going to be able to solve the original problem. So that's going to be a cool little technique, and it's a technique that we can use in lots of areas of math, and we do use in lots of areas of math. In particular, when we get to calculus, we use a lot of use substitution in calculus when we say, all right, I know how to solve a type of problem easily. This one almost looks like it. Let me do some substitution until it actually looks like it. And then we're also going to get to some word problems in the end that lead us to some quadratic equations. So that's our game plan. Let's go ahead and get into the first example now of review problems. The first review problem I want to look at is a problem that involves a square root. And so we should remember that when we have a square root, we're going to undo that by squaring, but we want to get this square root by itself first. So in this problem, I would start off by subtracting the x to the other side. And then I'd multiply both sides by -1, making sure to distribute the negative on that right-hand side. So now that I have this square root by itself, I can go ahead and square both sides. My blue ink's not working. There's my blue ink. So we're going to square both sides, but also remember that squaring both sides isn't fully legal. And so as soon as we square both sides, we have to make our note to ourselves that whatever we do, we need to check our answer or answers in the end. Left-hand side is easy to square because we're squaring a square root. On the right-hand side, we've got to do the whole a squared plus 2ab plus b squared thing, or you could FOIL that out. So now that we have this quadratic, we see an x squared, the first thing we want to ask ourselves is, can I easily get a perfect square on one side, number on the other? And the answer is no. So I'm going to get everything to one side, so the other side is 0. I'm going to subtract the 2x over. So now I'm going to say, can I factor this? That's the next step in our easiness steps, is can I factor this? Is there anything that multiplies to be 16 and adds to be -10? And there actually is. So this is x minus 8, x minus 2 would work, meaning x minus 8 could be 0, or x minus 2 could be 0. So x could be 8, or x could be 2. And so this one, as far as review, could have actually been given back when we covered the radical equations. But I want to point this out because instead of using the quadratic formula, factoring really was easy in this case and got us to our two potential answers pretty simply. Now we do still need to check each of these potential answers. We need to check x equals 8 as well as x equals 2. When we check 8 in the original, we get 8 minus the square root of 16 is supposed to equal 4. So 8 minus 4 equals 4. That's true, so x equals 8 is a good answer. Let's see if x equals 2 is also a good answer. So we're going to get 2 minus the square root of 4 is supposed to equal 4. 2 minus 2 equals 4. That is not true. So x equals 2 is not a correct answer. And x equals 8 is. And so really this is truly a review problem. We could have did this back in our radical equations section, but I just want to go over it to point out that when we got to the quadratic portion over here, if that was not factorable, we could have used the quadratic formula and got an answer. Let's take a look at example 2. In this example, we have a rational equation, meaning there's x's in the bottom. So we want to remember when it comes to the rational equations that we should check our answer, but in particular, we need to make sure that whatever we get does not make the denominator equal to 0. So no matter what in our end, we can't let x equal 2 or -2, meaning if we do get 2 or -2, we got to throw those answers out. Now, in order to solve a rational equation, we say, hey, that sure looks like a fraction to me. Fractions suck. Get rid of the fractions. So we multiply both sides of the equation by x plus 2, x minus 2. Now remember that means put that x plus 2, x minus 2 into the top of each fraction. So just in the numerator. We're not trying to build up to a common denominator. We're trying to get rid of our denominator. And so we do that by putting stuff into the top that's going to divide out with the stuff that's in the bottom. So we're multiplying both sides of the equation by x plus 2, x minus 2. And we can see that x minus 2's divide out in the first fraction, x plus 2's divide out in the second fraction. So now in our first fraction, we can go ahead and just distribute the 5 across to get 5x plus 10. And in the second fraction, we can distribute the 4 to get 4x minus 8. And on the right-hand side, that's a difference of squares, and we have x squared minus 4. We can now combine like terms on the left. And we're going to move everything to one side because we do not have a perfect square equals a number. So we're going to subtract the 9x to the other side and subtract the 2 to the other side. So now we have a quadratic that's equal to 0. We should try to factor. If we're not able to factor, then we have to use the quadratic formula. Now we're not able to factor. There's nothing that multiplies to be -6 and adds to be -9. So we do have to use the quadratic formula. Notice that our middle coefficient is odd. And so the trick does not apply. We just got to plug it in with 1, -9, and -6. So we're going to get the opposite of b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. So as we simplify up here, we get 81 plus 24 underneath the radical. 81 plus 24 is 105. I don't believe there's any perfect squares that divide evenly into 105, so this is as good as we can get. Now, as I'm looking at this, I'm supposed to plug my answer back in. I'm supposed to check it, but I'm really checking to make sure it doesn't equal 2 or -2. Neither of these answers are 2 nor -2, and so these are my two answers. Now remember, when entering this in our homework system, you enter this as two separate answers to say there's the plus version and there's the minus version. So this example is pseudo review. So what I want to talk about in this problem here is we want to make sure that we're using factoring whenever possible. So this problem here is quite clearly not a quadratic. What I want to point out, though, is what not to do. What might be tempting to do in this problem would be to say, so don't copy this down, it would be to say add the 216 to the other side, and then take the cube root of both sides. And that would get me x equals 6. And if you plug 6 back into the original problem, it'll work. It will get you a correct answer. So that's fantastic, right? I very simply got the correct answer. Not quite. There's actually a total of 3 answers to this problem, not just the one. And we want to find all 3 answers. So we got to be a little bit careful here. What we did was fully legal and got us all of the real answers. The 2 answers that we didn't get were complex, non-real answers, but we'd like to find those as well. Now, a good kind of general rule of thumb to help you out to make sure that you don't accidentally do that kind of thing is if you look at the power that you're being raised to, your highest power in the problem, that's typically how many answers to expect. Now, if you go on to take the math class beyond this, you'll go ahead and learn a little more detailed version of this rule, but basically it's just kind of a rule of thumb at this point to say, if I have an x squared, I'm probably going to get 2 answers. If I have an x cubed, I'm probably going to get 3 answers. If I have an x to the 4th, guess what? Probably going to get 4 answers. And we are going to see those. We are going to solve some x to the 4th in a minute. But in order to find those answers, we want to factor. So we want to realize that what's going on here is I have an a cubed minus b cubed situation. So I want to factor this as a minus b times a squared plus ab plus b squared. We remember that from lesson 1? That was a review from our prerequisite course, as a matter of fact. So if we factor this, it factors as x minus, or sorry, x minus 6, I said the right thing, didn't write the right thing, x minus 6 times x squared plus 6x plus 36 equals 0. So I've now factored this to have parenthesis times parenthesis equals 0, which means either the first parenthesis is 0 or the second parenthesis is 0. Now if the first parenthesis is 0, I get x equals 6, which we already knew was an answer. We knew that this worked. But now we also have a quadratic that we need to solve. Now that quadratic's not factorable, so we're going to use the quadratic formula. With the quadratic formula, our middle coefficient's even, so we should divide both sides by 2. We should use that cool trick. So if we divide both sides by 2, then we can plug in an a value of 1/2, a b value of 3, and a c value of 18 into the quadratic formula. And that's going to get me the opposite of b plus or minus the square root b squared minus 4 times a times c all over 2 times a. Now if we do a little simplifying, 4 times 1/2 is 2. 2 times 18 is 36. And our denominator is just 1, so I'm not going to bother writing it. Nine minus 36 is negative 27. So now with that radical, I'm going to do the whole break it up, take the radical, clean it up thing, where I can break it up as 9, negative 1, and 3. Square root of 9 is 3. Square root of negative 1 is I. And then square root 3. Now don't forget that we still have that answer of x equals 6 from way up there that we got to report still. But this gives our 3 answers to our x cubed, because we have one answer of x equals 6, and then we have answers 2 and 3 from the plus minus there. And so that gets us our 3 answers. Here's a different third degree or cubic equation that we're going to try to solve. And we're going to do the same thing as we did in the last cubic, which we're going to try to factor. So we're going to factor this one in a different way, though, because if we count how many terms we have, there's 4 terms. So this, again, is going to go back to our first lesson on factoring, where we're going to remember with 4 terms we factor by grouping. We factor a GCF of x out of the first group. We factor a GCF of negative 3 out of the second group. And we notice that we're left with x squared plus 1 from each. So that means I could factor a common factor of x squared plus 1 out. It would leave me an x from the first group. It would leave me a negative 3 from the second group. So now I have parenthesis times parenthesis equals 0, which means either the first parenthesis is 0 or the second parenthesis is 0. Now the second one is super easy. We add the 3 to the other side, x is 3. Now for the first one, let's go back to the first thing we talked about in this lesson about breaking down your easiest way to solve a quadratic. Can you get perfect square on one side, number on the other? And we absolutely can. We can just subtract the 1 to the other side. Now we have a perfect square on one side, number on the other. To solve this, we take the positive and negative square root of both sides. And of course, the square root of negative 1 is I. So this gets us our 3 answers we were expecting. We're getting positive I, negative I, and 3. Now we're going to shift gears into our use substitution portion of this lesson. So what we're looking at now is an example that has an x to the fourth in it. And so we know we're going to expect 4 answers. Now the clue that this is a use substitution-y type problem is when we look at what the variable is and look at the fact that the other variable involved is that guy squared. So if we're looking at the fact that the one variable is x squared, if I squared that, I get the other guy. So I know that that's a really weird, I use a lot of pronouns with this and guy and things like that, but that's where you sort of just got to blur your vision a little bit, squint your eyes a little bit and say, whatever's going on here in the middle, the other guy is that guy squared. If you see that going on, then that's an indication that maybe you should use substitution on the problem. And what we're going to do with use substitution is we are going to create this variable u, and we're going to let him be the middle variable, or really the middle expression. Not with the coefficient, just whatever the variable is that's going on. So we're going to say, let's let u be the same thing as x squared. So that means everywhere that there's an x squared in the problem, we can replace it with a u. So that means that this can be 5u. The minus 4 doesn't change at all. The equals 0 doesn't change at all. Now for the x to the fourth part, well, if u is x squared, then if I squared both sides, u squared would be the same thing as x to the fourth. So 9x to the fourth is the same thing as 9u squared. So all we've really done is we put a costume on this problem. We said instead of x squared, let's just call it u. We're going to use u as a middleman. We're using it as a middleman because we're transforming or disguising our problem as an actual quadratic. So now it looks like it's a quadratic. I have something squared plus something plus a constant equals 0. Pretty easy. So now I can actually factor this. And I'm going to tell you, when it comes to these use substitution problems, I'm going to make sure they're always factorable just to make your life easy. So on this one here, let's go ahead and try to solve this guy. We got 9u minus 4 and then u plus 1. This would factor it nicely. So now either my 9u minus 4 could be 0 or my u plus 1 could be 0. I add the 4 to the other side, divide by the 9 so that u is 4/9 or u is -1. Now keep in mind, if you look back at the original problem, our original problem didn't have a u in it. We made the u up. So we definitely don't want to answer this problem with our u in it. We need to answer what x is. So now that we know that u is the same thing as 4/9, we're going to come back over to my right-hand side here and say, well, if u is the same thing as x squared, then x squared must be 4/9. If u is -1, then x squared must also be -1. So we're going to always come back to our substitution that we did, and we're going to replace the u with whatever it is that we said u was equal to. And that's why we need to write it down too. We need to write down let u equal x squared. It's going to help us out. So now we have these two new problems to solve. We're going to ignore everything else in the problem, and we're just going to focus in on what's going on here. We're going to say, I want to solve x squared equals 4/9. Well, that has a perfect square on one side, number on the other, so I can use the square root property. I can take the positive and negative square root of both sides. And I can do the same thing here. I can take the positive and negative square root of both sides. So that's going to get me positive negative 2/3. That's going to get me positive negative I. So as far as our homework system, that means we have 2/3, comma, negative 2/3, comma, I, comma, negative I. This gets us the 4 answers that we were expecting for our x to the 4th problem. Now again, we defined what u was to turn this into an honest-to-goodness quadratic. We solved the honest-to-goodness quadratic. Then we put it back in terms of x instead of u. And then we solve those equations. And that's going to be the process in order to use u substitution. In our next couple examples, we'll look at other variations to u substitution as well. Here's another example of where u substitution is going to come into play. And again, we're going to notice that there is some sort of variable, and then the other variable is that squared. So if we were to let u be x to the 1/3 power, which remember means the cube root, then that would mean if I were to square both sides, u squared would be x to the 2/3. So this allows us to rewrite the original problem as 3u squared plus 11u. Now we're going to go ahead and subtract the 4 to the other side right now, since we know that that's what we're going to end up needing to do. And now we have an honest-to-goodness quadratic. Now we can go ahead and factor this. So this factors as 3u minus 1, u plus 4 equals 0, meaning either 3u minus 1 could be 0 or u plus 4 could be 0. Now if I add the 1 to the other side and then divide by 3, I get 1/3. I can subtract the 4 to get negative 4. Now again, we're not looking to figure out what u is equal to because we made up u. We're looking for what x is equal to. So we got to come back to what we did for our substitution and say, instead of writing u equals 1/3, u is the same thing as x to the 1/3 power. And similarly, instead of saying u equals negative 4, instead of that u, we're going to write x to the 1/3 power. Now, we've got to be a little bit careful here. I see a lot of mistakes happen with these types of problems. We got to remember that we're solving a brand new equation. We're not looking at this to say 1/3 means cube root, so it's cube root 1/3. We're saying that the 1/3 power means the cube root, so the left-hand side is cube root of x. And now we want to say, how do I solve this? How do I get the x by itself? How do I undo the cube root? I undo the cube root with a cube. So I actually need to raise both sides to the 3rd power in order to undo that cube root. This gets me x equals 1 over 27, x equals negative 64. And those are my 2 answers. Now this example is actually really nifty. It's nifty because we can actually use 2 different methods of solving this that we've already talked about. So I'm going to go ahead and show you both methods so you can kind of see which one you'd prefer. Now one way is with u substitution to say I see some sort of variable and I see that variable squared. And again, that's our clue that u substitution is a possibility. So if I let u be x to the negative 1st power, then that would mean that u squared would be x to the negative 2nd power, meaning I could rewrite this problem as u squared minus 8u plus 7 is 0, allowing me to factor this as u minus 7, u minus 1, meaning u minus 7 could be 0 or u minus 1 could be 0. Therefore, u is 7 or u is 1. Now, in order to solve for x, instead of u equals 7, remember that u is the same thing as x to the negative 1st. And instead of u equaling 1, u was the same thing as x to the negative first. Well, what does x to the negative first mean? X to the negative first means take the reciprocal. How do we get the x by itself on the left? Well, one way to do that would be to take the reciprocal of both sides. Now the number 7 we can think about as 7 over 1. So when I take the reciprocal, I get 1/7. Over here, as I take the reciprocal of 1 over x, if you flip 1 over 1, you still got 1 over 1. So we get our two answers of 1/7 and 1. So that was one approach to solving this problem. Another approach we could take to solving this problem is actually to treat this like a rational equation. From the beginning to say x to the negative second means 1 over x squared. X to the negative first means 1 over x. So at this point we could say fractions suck, get rid of the fractions. Multiply both sides of your equation by x squared. So that puts an x squared into the top of every fraction. That gets me 1 minus 8x plus 7x squared. Or if I want to write this a little bit differently, I could write it as 7x squared minus 8x plus 1. And now I'm going to factor this as 7x minus 1 times x minus 1, so that either 7x minus 1 is 0 or x minus 1 is 0. So the x is 1/7 or 1. And so we can see that we get the same answer either way, whether we treat this like a rational equation or whether we treat it like a u substitution problem. All right, so let's move into some word problems now. So this problem tells us Josh Smith's workout consists of jogging for 3 miles, then riding his bike for 5 miles at a speed of 4 miles per hour faster than he jogs. If his total workout time is 1 hour, find his jogging speed and his biking speed. All right, so there's a lot going on in this problem, quite clearly. What does jump out at me in this problem as far as trying to organize my work is I see miles, miles per hour, miles, and we're being asked for a jogging speed. So as I'm looking at all this information, what's jumping out at me is distances, rates, and times. So I'm going to try to organize my information in what we've called a dirt box, a D equals RT box, so I can just try to figure out what information do I have, what am I looking for. So as I look at distance equals rate times time, and I create this box for organizing my information, I have two situations. I have the jogging situation and the biking situation. I'm going to try to jot down some information about each. So for jogging, we're jogging for 3 miles. Miles measure distance. So I'm going to put 3 in for my jogging distance. It's a little cell there. And then rides his bike for 5 miles. Also, with the bike, miles is distance. So those are values that we just straight up know. Now we do know that the biking speed is 4 miles per hour faster than the jogging speed. Now we don't know what the jogging speed is, and in particular we're asked to find his jogging speed and his biking speed. So we need a variable for it. So we need a variable for the jogging speed. Now we do know that the biking speed rather is 4 miles per hour faster than he jogs. So 4 miles per hour faster would be x plus 4. Now be careful not to put 4x, because remember 4x would mean 4 times as fast. And that's not what it said. It just said that we're 4 miles per hour faster, so that's addition. Now we don't know anything individually about the workout time, but we do know that combined it's 1 hour. And we have two different ways of dealing with this. We could use a second variable if we wanted to, where we do the whole y and 1 minus y thing, but that's going to lead to an ugly situation I don't really want to deal with. So instead, what I'm going to do is I'm going to just jot down a little note that if I take the time that he jogs for and add that to the time that he bikes for, if I add those two things together, I'm going to get 1. So we know the equation d equals RT, but what if I want to solve that to get the t by itself? I could divide both sides by r, and that would say that time is distance over rate. So the time that he jogs for would be the distance he jogs for divided by the rate at which he jogs. The time that he's biking for would then be the distance that he's biking divided by the rate at which he is biking. And when I add those things together, I get 1. So as I look at this, what I see is a rational equation, an equation with fraction expressions in it. Fractions suck. Get rid of the fractions. So we're going to multiply both sides by the LCD, where the LCD is x times x plus 4. And so we're going to put an x plus 4 into the top of each of these fractions. And the goal here then is to get rid of the fractions. That's the whole idea. So in the first fraction, the x's divide out, leaving just 3x plus 12 as I distribute the 3. In the second fraction, the x plus 4's divide out, just leaving the 5x. And on the right-hand side, I could distribute the x across, getting me x squared plus 4x. On the left-hand side, we can combine our like terms, and then we can bring everything to one side so that the other side is 0. At this point, we could try to factor. If we can factor, awesome. If not, we use the quadratic formula. And in this case, we actually can factor, so don't forget to try that. So that's going to give us that x minus 6 could be 0, or x plus 2 could be 0. And so x could be 6 or negative 2. Now the negative 2 gets thrown out because remember that x, if we look back up top, x was the rate at which we jog. You can't really jog at a negative number of miles per hour. That doesn't make sense. With x equals 6 being our answer, let me jot that down up here. We still need to actually answer the question that was asked of us. And we actually had 2 questions, to find the jogging speed and the biking speed. So we wanted the jogging speed and the biking speed. And this is, again, why we like to organize our information in a nice, smart way. Because we can clearly see the label that x is the speed at which we jog. So that's 6 miles per hour. And the rate at which we bike was x plus 4. It was 4 miles per hour more than that. So that would be 10 miles per hour. And that makes it really easy to answer the actual question that's asked of us if we organize our information well. Now, the last type of problem we're going to look at in this lesson are work rate problems, where a work rate problem is when 2 people or 2 things are working together to accomplish the same job. But when they're working together, then they make the job easier. And so we're going to do some calculations, such as finding how long it takes them to complete the job together or something like that, or how long it would take one of them alone if we know how long it takes them together. We're going to do some different calculations with that. So when you're dealing with one of these work rate problems, there is an underlying formula that's right there in your notes, and it's right here on the screen, where it's 1 over the time of one of them alone, the time it takes for them to complete the job if they were doing it completely solo, plus 1 over the time it takes the other one completely solo. So if we had person A and person B, or let's say Alex and Brad. So if we have Alex and Brad working on this job together, then T sub A is Alex's time alone, how long it takes him to complete the job. T sub B is how long it takes Brad alone. So if we take 1 over the time of A plus 1 over the time of B, that's going to equal 1 over their time together. So if you want to just straight up memorize this, that's great. And this is actually written in a form that's easy to memorize. Now I'm going to show you where this formula comes from. So I just want to point out that it's not some formula I just pulled out of thin air and said, memorize this because I said so. So I want to show you where it comes from using some hopefully simple logic. If you want to copy this down into your notes, you can. I didn't give you room to work on it, but if you want to do it on the back page or on a scrap sheet, you can. Or you can just sort of follow along to say, yeah, I believe you. That makes sense. So to show where it comes from, this is all going to come from a very basic formula. It's actually a more generalized version of distance equals rate times time. It's actually amount of anything equals the rate at which you're doing it times the time. So distance just happens to be if the rate is in miles per hour or feet per second. But in general, if you have a rate of something per unit of time, so keep in mind that rates are something over time, so it's miles per hour or something like that. So actually, to make it more generic, I would probably call this amount per unit of time, so miles per hour, feet per second, something like that. Well, if you're multiplying that by the time divides out and you're left with amount. So hopefully it's clear that a nice generic formula is amount equals rate times time. So if we're talking about T sub A as the time it takes person A to finish the job alone, let's talk about their rate. So let's talk about the rate of person A. If I take the rate times the time it takes them alone, they should finish one job. So our rate is going to be in jobs per hour. So if I want to figure out what that person's rate is, I would divide both sides by their time, and their rate is 1 over their time. The units here are going to be something like jobs per hour, something along those lines. But the rate at which person A works is 1 over their time alone. So if I took the amount of the job that person A does, and I add that to the amount of the job that person B does, that should add up to 1. Hopefully that's clear and obvious. What that's saying is if person A finishes 2/5 of the job, then person B needs to finish 3/5 of the job. We need to add those together to finish the job. So if we take the amount of person A plus the amount of person B, that should equal 1. Well, their amount that they finish is going to be their rate times their time. So if I take the rate of person A times the time that they're working together for, so this is, again, when they're working together. And similarly, if I take the rate that person B works times the time that they're working together, they should probably finish the job. But we just saw that someone's rate is 1 over their time alone. Let's get to that in a second, though. Before we get to that, I'm going to divide both sides of this equation by their time together. Now, this isn't a necessary step. This is just what we do to make the formula easy to memorize. So in doing so, the time together divides out, the time together divides out, and we have the rate at which person A works plus the rate at which person B works equals 1 over the time it takes them together. But the rate at which person A works, we discussed earlier, is 1 over their time alone. The rate at which person B works would then be 1 over their time alone. And that's how we get this formula here. So you should have this formula memorized. You will definitely need it. This is where it comes from. Again, this might help you if you can't memorize it, that you can come up with it on your own. But again, I also just want to make sure that you knew this is not something I just pulled out of thin air. Let's look at an example problem of a work rate problem. So as I read this, we're told that a water tank on a farm in Texas can be filled with a large inlet pipe and a small inlet pipe in 3 hours. The large inlet pipe alone can fill the tank in 2 hours less time than the small inlet pipe alone. Find the time to the nearest tenth of an hour that each pipe can fill the tank alone. So, before we even get into this problem, I do want to talk about a common sense estimate so that we can get a ballpark idea of roughly what our answer should be. So what I like to start with is I like to start off with saying, what if they had equal speed or equal rate? So if they had equal speed or equal rate, and it took them 3 hours together, then each one would be 6. So what some people do is they say that it's 1.5 for each, but that wouldn't make any sense. We got to think about the fact that if they're working alone, so that's what we're looking for here, is we're looking for their time alone. So if we are looking at their time alone, it's got to be more than when they're working together, not less. It wouldn't make sense that alone they can do it even quicker. Now, that's our start to our common sense estimate. That's not actually going to be our common sense estimate, because we're going to say, well, the large one is faster. It's taking less time. So it's going to be a little less than 6 for the large inlet pipe. But that means that the small one needs to be even more. So maybe 5 and 7, something along those lines, because that is a 2-hour difference, but the large one can do it quicker. So that's the way that I would kind of get a ballpark estimate, is to say, well, what if they were filling it at the same rate? What if they worked at the same speed? How long would it take each one of them alone? And then look at the fact that, okay, well, the large one takes less time, so let's drop that number a little bit, make the other one a little bit bigger. Gets you a ballpark estimate just to see if our actual answer ends up working. Now we know that in order to solve this problem, we're going to use the formula 1 over the time of one of them alone. We'll go ahead and say big, plus 1 over the time of the other one alone, we'll call it small, equals 1 over their time together. We know that's the underlying formula for this problem, which means I need to figure out either values or variables for the time that it takes the big one alone, the time that it takes the small one alone, and their time together. Now their time together is straight up given to us as 3 hours. Now as far as the other values, we know that the large inlet pipe can fill the tank in 2 hours less time. So if we call the small one x, then the big one is 2 hours less than that. So it's x minus 2. So now we can plug those values into our formula to say we have 1 over x minus 2 plus 1 over x equals 1 over 3. This looks to me like a rational equation, an equation with fractions in it. And as you know, fractions suck, so get rid of the fractions. We're going to multiply both sides of the equation by the LCD. So that means we're going to put the LCD into the top of every fraction. Again, not the bottom. We're just putting it in the top because our goal is to get rid of the bottom, to get rid of the fractions. So in the first fraction, the x minus 2's divide out, leaving just the 3x. In the second fraction, the x's divide out. As I distribute the 3, I get 3x minus 6. And on the right side, the 3's divide out. And if I distribute the x, I get x squared minus 2x. I can combine like terms on the left, and then bring everything over to the right. So I have this quadratic equation to solve. Now this quadratic equation is not factorable, so I am going to have to use the quadratic formula. I go ahead and use the trick, even though we're probably going to use a calculator anyhow because we want to get some sort of decimal answer. It usually makes more sense on word problems. It wouldn't make sense on a word problem to say It takes square root of 2 hours. You actually want to put it in the calculator and give a more reasonable answer. So I divide both sides by 2 so that my A value is 1/2, my B value is -4, and my C value is 3. And I plug into the quadratic formula of the opposite of B plus or minus the square root of B squared minus 4 times A times C all over 2 times A. Let's do some simplifying now. We'll do the calculator in a second, but I think that if we plug as little into the calculator as possible, we're less likely to type stuff wrong. So I've got 4 times 1/2 is 2, 2 times 3 is 6, and in my bottom, 2 times 1/2 is 1. And this is why I wanted to use the trick on this problem. It's really going to make it easier to plug in. So I'm going to plug two things in my calculator. I'm going to plug in 4 plus the square root of 10, and I'm going to plug in 4 minus the square root of 10. So off screen, I'm going to grab my calculator because these are not hard things to plug in the calculator, so I don't think you need to actually see this calculation. When I do 4 plus the square root of 10, I'm getting about 7.2. When I do 4 minus the square root of 10, I'm getting about 0.8. Let's go back up to how we defined each of these values. So remember 7.2 and 0.8 were the two values that I got. So X was the time for the small pipe alone. Let's look at our estimates, 5 and 7. We estimated 7 as our ballpark figure. One of our answers is close to that. One is not. Let's look at why that's the case. Let's look at what happens if I let X equal 7.2 versus what happens if I let X equal 0.8. The time of the big guy, if X is 7.2, would be 2 less than that, or 5.2. If I let it be 0.8, 2 less than that, well, 0.8 minus 2 is negative 1.2. That's not good. I can't have a negative time. So my answer of 0.8 doesn't make sense in this case. I got to throw it out. And so my large inlet pipe, or my big one, could fill this in 5.2 hours alone, and the small one could do it in 7.2 hours alone, which fits into my common sense estimate really nicely. My guess of 5 and 7 was pretty close to being dead on.